So, just some history. There was maybe 4 years ago a winter school in Brasilia where the goal was to present the topic of unconventional superconductors to a group of graduate students. And so that's the level at which this is going to be. It assumes not so much knowledge in unconventional superconductivity, maybe a little bit. And then I went and to visit Stanford for a week, and Steve Kivelson suggested that I do something like that there. But there was a lot of interest in strontium ruthenate. And so I focused the efforts towards strontium ruthenate. And again there, the focus was to present it to graduate students who were somewhat new to the field and perhaps working in other areas like spintronics or something else. All right, and so what I'm doing essentially is giving a shortened version of what I gave at Stanford. That's what I'm doing right now. So otherwise I think maybe people become oversaturated with talks if they do the whole thing. So this, I hope, will get done in a couple hours. Not today. It should be broken up today and tomorrow. Maybe I'll get it done today. We'll see how it goes. Right. So let's begin. So what I'm going to first cover then is just a brief overview of conventional and unconventional superconductors. And one of the things we're going to be interested in fact, the main goal of all of this, will be to just talk about the development of the Landau theory for unconventional superconductors. And the Landau theory is entirely symmetry-based, and so we'll go through some group theory to talk about how this is done, in particular some simple examples of groups and representations of groups to give you a feeling for the ingredients behind the Landau theories. And then when you have a Landau theory, you have a series of phenomenological parameters which are undetermined. And it turns out for multi-component unconventional superconductors, when they're undetermined, you have many possible phases. And so you'd like to do something to specify them. And we actually have a very powerful theory that allows us to determine these coefficients. And so I'll talk about how you can determine those coefficients within a weak coupling theory, and also talk about some of the general symmetry properties of pairing potentials in this weak coupling theory. And then I'll look at a particular example, in particular a P plus IP spin triplet superconductor, and just look at how the theory applies in that case there. And then maybe I'll talk about some other symmetry-based properties that come along with this. All right, and then I should really thank Manfred Siegerist here, because he provided many of the PowerPoint slides that I'm showing here, so they're actually his. I've altered them, of course, but he deserves a lot of thanks for that. All right, so just some very elementary review then, and I think everybody here is familiar with this, but just to make sure everyone's on the same page. If we look at conventional superconductors, we have two descriptions, right? One is Ginzburg-Landau theory. Okay, everything I'll be talking about today is mean field, by the way, so we won't talk about fluctuations. I mean, you can use the free energy functionals to determine fluctuations, but we won't talk about them. All right, so we know that there's a phase transition associated with an order parameter. This order parameter breaks gauge symmetry. It's 0 above Tc and grows continuously from Tc and is non-zero below Tc. And so we describe that by a free energy functional. And here the order parameter has a phase and an amplitude. And the free energy functional in the homogeneous case has two terms. It has a coefficient A of t and then a constant and a coefficient b, which doesn't depend on t in the Ginzburg-Landau limit. And the important feature is that A changes sign, right? And so as A changes sign, the minimas of this, when A and B are both positive, the minimum is given by psi is 0. When A is negative, B is positive, you get some non-zero psi solution. And so above Tc you get this behavior, below Tc you get this behavior, and you get a finite amplitude for the order parameter. And then on top of this, we can add the role of magnetic fields, and that I've shown down here. You can have spatial variations of this order parameter, plus you can have a vector potential, or the h² term for the magnetic fields, and then you minimally couple the spatial variations with the magnetic field in the following way, much like we do in graduate quantum mechanics courses. So this is an overview of what we see for the Ginzburg-Landau theory, and again, I'm not going to talk about the details behind this, maybe a little bit later on, depending on how much time things take, etc. All right. The nice thing about conventional superconductors is we also have a microscopic theory. So I'm going to spend maybe a little bit more time on this, because this might be where people in cold atoms may not be as familiar with things. All right, so BCS introduced the idea of an energy gap, which I've given here, and this corresponds to a Cooper pair. So a pairing of two electrons, one with momentum k spin down, one with momentum k minus k spin up. And actually, throughout this talk, there's one thing I'd like you to keep in mind. So here I've just drawn a two-dimensional Fermi surface. The yellow states are filled, and then the white states are empty. And we're going to be talking about the weak coupling limit explicitly. And so what that means in the weak coupling limit is that we're going to have a delta that depends on k, and that k is just going to be on the Fermi surface. So it's just going to alternate as we go around here. So in particular, for this conventional superconducting case, this delta is k independent, meaning it's the same everywhere on the Fermi surface. And these two red lines denote the energy gap. All the single quasi-particle states are gapped here. All right, so if you look at the single particle density states, you find there are no excitations up to the gap, then you get a square root singularity in density of states, and then you get something that approaches the usual density of states there. All right. So again, I'm going to show these pictures then of Fermi surfaces perhaps later on. And then, again, delta is defined on the Fermi surface and will vary with k. Okay, so in the weak coupling theory then, we have a finite energy gap. You can see it in the quasi-particle spectrum, the Fermi spectrum, and it has some very clear consequences. For example, in any thermodynamic probe at low temperatures, you'll get this characteristic exponential delta over kBT behavior. And so that's an easy way to see that you have an S-wave superconductor forming. And also, for this particular case here, these are two fermions. And so if I interchange these two, I have to pick up a minus sign. I've already told you that it's constant in k space, so nothing happens when I take k to minus k. And that must tell me that I have a spin singlet Cooper pair here. So spin up, spin down, minus spin down, spin up. And because I have a spin singlet Cooper pair, I'm taking all my fermions and making spin singlets from them. Spin singlet objects have no spin and can't react to a magnetic field. And so when you measure the spin susceptibility, then, which is the response to a small magnetic field, then you see that in the usual Fermi state you have a Pauli susceptibility, but then it drops as you enter the superconductor down to zero at zero temperature in the simplest explanation, because the Cooper pairs carry no spin. All right, so this is some properties you get from the microscopic theories of conventional superconductors. And then one last property. So I'm going to contrast this in a couple minutes with unconventional superconductors to show you that some new properties show up. And so I thought it'd be also interesting to show some very famous experiments in the Josephson effect for unconventional superconductors. And so here's just an overview of the Josephson effect. If you don't know the details, it's not so important. So here we have two superconductors, and they're weakly coupled through this insulating barrier. And so then you can just look at the IV characteristics of this junction, and then at zero bias across here, you find that there's a finite current flowing, and that's the Josephson current. And then as you increase the bias, eventually you begin to break Cooper pairs, and then you get a normal current flowing as well, in plus and minus. And so that's the simplest picture. Now you can also look at the behavior of this Josephson current as a function of magnetic field. So you put a magnetic field in this junction, and so you have a finite flux coming through here. Then you find that the Josephson current has a very typical behavior. With zero magnetic field in the junction, you have a peak, and then as you increase the magnetic field, or the flux through the junction, you get this Fraunhofer type pattern. And so this is something that will contrast to unconventional superconductors in the next slide. All right, so why do we study unconventional superconductors? Well, the reason is that there are a whole series of experiments that show there's really non-trivial behavior, which is quite different than conventional superconductors. And so here's some examples of that. Here is the very famous corner junction experiments from Dale Van Harlingen's group at Urbana-Champaign. this is a Josephson junction wrapped around a corner. So in principle, this is an insulating barrier here, and this is two superconductors. And now, if they apply a flux through the junction, what they get is not the usual Fraunhofer pattern, but instead of zero flux, they get a minimum. And then as they add more flux to the junction, the critical current increases and then goes down. All right, and so it was not clear, you could clearly not understand this from a conventional S-wave superconductor. And then there's uranium-platinum-3. Uranium-platinum-3, if you look as a function of magnetic field and temperature, it shows a wide variety of phases. So in particular, at zero field, you find that there are two phase transitions in the superconducting state. And there's no way you can understand this from a conventional superconductor. In fact, this has to be a multi-component order parameter. And then there are the very famous experiments of Hardy and co-workers in British Columbia, where they, I should mention, this is results from people at Northwestern in Milwaukee as well, where they measure this phase diagram with these multiple phases. And then in Northwestern, here I'm showing the variation, the penetration depth. And I'm not going to tell you in detail what that is right now, but the important point is it's a thermodynamic property. And so if it's a thermodynamic property and you look at low temperatures, you expect it to be exponentially gapped. But when you look here at low temperatures, you see something that's very linear in temperature. And this tells you that this is not consistent with the way we understand conventional superconductors. So this is actually one of the very first, these two experiments, I think, by and large, convinced most people that the high temperature superconductors are what is known as a D-wave superconductor as opposed to a conventional case. And then the material I'll be talking a little bit more about, which is strontium ruthenate. Here I'm showing you, in essence, the spin susceptibility is a function of temperature. Right? So I told you before, for conventional superconductors, you have spin singlets. Spin singlets cannot respond to spin. But here, if you look at strontium ruthenate, here you have your poly spin susceptibility. But as you go through TC, you see no change at all. And so this is one of the first two experiments to tell people that this was not a conventional superconductor. And in fact, the way you can have this is that your Cooper pair is not spin singlet, but spin triplet. This is what you would expect if you had a spin singlet, according to, this is from Kenji Ishida and co-workers in Kyoto. All right, and then a little bit more about strontium ruthenate, which is drawing a lot of interest these days. And that's that there's evidence for broken time reversal in the superconducting state, something you wouldn't expect at all for a conventional superconductor. And the way people find this is they look at, well, they look at the muon relaxation rate. So they put muons inside their superconductor and they watch how the spins relax in this case. The muon's spin depolarizes. And what they find in the normal state is some depolarization that looks like this. But as they enter the superconducting state, they see a dramatic increase in this depolarization. And the interpretation of that is that there's locally magnetic fields being created, and the only way you could do that is through breaking time reversal symmetry. Yeah.
You see, I want to ask about the spin triplet you mentioned for the pair. So, if it's spin triplet, then the orbital should be odd momentum.
Yes, that's right. That's right.
But so that's not the D wave.
That's not. No. It's a P wave. P plus IP.
Okay.
Actually, so here that's the conclusion that you'll get from these two experiments.
Question regarding that last comment. How do we know it's not some other?
It could be, so, how do we know it's not some other, sorry, which P-wave state?
Yes. Not
okay.
necessarily PX plus IPY, but say just PX or just PY.
Okay, this is, so, okay, maybe the answer to that are these more recent experiments by Aaron Kapitolnik and co-workers where they measure the polar Kerr effect. So the reason this is an interesting question is that I said that there are local moments that suggest the state breaks time reversal symmetry. But if you have local disorder, you could actually have locally broken time reversal symmetry, and then the bulk of your system could be time reversal invariant. All right, and so what you need to see is something that tells you that the bulk of the system breaks time reversal as opposed to just locally. So this is consistent with a broken time reversal symmetry, but not actually proof. And so these more recent polar Kerr effect experiments of Aaron Kapitolnik, and I'm not going to go into the details here, give stronger evidence for both broken time reversal symmetry. Yeah?
But if it's PX, wouldn't it be gapless actually?
px plus I py.
So
We're going
to
yeah.
look for basically signs of the gapless quasi-particle instead of doing this curve. If you believe that it's any p wave, so
Well, px plus I py is gapless because the magnitude is px
Right,
plus
but-
py squared.
yeah, I'm just talking about the question whether it's px plus ipy or just px.
Yeah,
Px is
okay,
gapless,
so
you can distinguish those two.
that's true, you're right. You can distinguish those two. And that's a good point. Now, there is evidence, so the story's a little bit complicated there. This is a multi-orbital system, so in principle it could be two-gap superconductivity, and there's evidence for low-energy excitations. And the question is, what is the origin of those low-energy excitations?
So they basically do see gapless excitation.
Well, it's never clear if it's gapless or gapped, so that's the issue. Well, we can go into this later. So if you have two gaps that are different by factors of 10, for example, how could you tell it was truly gapless? So this question is still open. Anyhow, that's an aside.
Right. For a non-expert, why do you say that these curves prove that time reversal is broken?
So this suggests that there's some sort of local magnetic moments which are leading to depolarization of muons in the superconducting state. So that means as you go below Tc, there's some sort of magnetism forming. And the only way you do that, in principle, is by breaking time reversal symmetry.
But it could be anti-ferromagnetic.
It could be, but then why would it show up exactly at Tc? Why would the Tc of antiferromagnetism and superconductivity be the same? Right? So certainly there's many objections you can raise, but perhaps the most reasonable explanation is the superconducting state itself is breaking time reversal symmetry. And in fact, if you have other explanations, it'd be nice to discuss them and explore them. All right. So these two experiments then, on the previous slide, the fact that the spin susceptibility doesn't change entering the superconducting state, and then the evidence that the superconducting state breaks time reversal symmetry, leads to a particular spin triplet state with an orbital dependence px plus ipy. And so we're going to talk about how this can come about from macroscopic theories and how we can understand this, and ask if this is even a natural state to appear in these cases. Yes.
So in other words, px alone doesn't break the time reversal symmetry of
That's
p.
right. Yeah,
So
yeah.
this is one reason why you have px.
That's right, exactly. The I is from the broken time reversal symmetry. Spin triplet means it's p wave in principle. And so that's where the p comes from. So these two experiments then suggest this. Okay, so that's my motivation for studying unconventional superconductors with multiple degrees of freedom. And in case you don't know, these p plus ip states have become very topical recently because they support things like Majorana modes in the cores of vortices. And so these are zero energy states that obey non-trivial statistics. And so there's a lot of maybe false hope that you can exploit this in some way to make quantum bits. But nevertheless, those states by themselves are interesting. And so people are quite interested in the possibility of p plus ip. All right, so with that motivation, I'm now going to switch topics a little bit, and I'm going to slow down quite a bit and talk about Landau theory and group theory, and talk about how we first define superconducting states within a Ginzburg-Landau type theory. All right, so Landau pointed out that to describe a phase transition, you have to have an order parameter, but he said that these order parameters belong to irreducible representations of the normal state symmetry group. And so to understand that fully, I have to explain to you what irreducible representations are. And so I'm going to do that, but in principle, there's some basis functions, right? So this is some basis for an irreducible representation. Psi1, Psi2 is a function of k. And remember again, k is on the Fermi surface, so we have a cylindrical Fermi surface. This just tells you how Psi1 changes as we move around on that Fermi surface. And what we do is we expand our, in this case, our gap function in terms of our order parameter components, which I'll call eta sub n, times these basis functions defined on the Fermi surface. And the Ginzburg-Landau free energy is a functional of these order parameter components. All right. And so the way you do it is once you understand the particular representation or irreducible representation your superconducting state is appearing in, then you write down a free energy functional that is a scalar under all the symmetry properties of the particular normal state symmetry group. Right? And the important point is that each irreducible representation has a different TC. And so if you see a single TC in a superconducting state, it belongs to a single representation.
But not necessarily if you have a homogeneous distribution of, let's say, one of them, it can generate a small component of the other one.
That's true. Okay, so the linear problem at TC will have only one representation. You're right. You can, in principle, induce other ones as you go to more nonlinear terms. All right. So what I'm going to do now then is take a long detour before we come and discuss these three energies, and then talk about group theory, and then talk about what irreducible representations are. And you'll get a feeling for some of the language that people use in the field of unconventional superconductors. And you'll see why it's actually quite misleading at times. But, you know, we have to make our own shortcuts. All right, so let's begin. Well, I think everybody knows this, but let's begin with defining a group. So that's a set of elements A, B, C with a multiplication rule that assigns to each ordered pair, A, B, another element, which we write as without the comma in there. And then it satisfies these three properties. A times BC is AB times C composition. There exists an identity, and the identity gives the same. So A times E is E times A is A, and E is the identity, and there's an inverse. So it's a closed set of elements, so when we multiply the two, we get another element to the group, and then we have these other features here. So I think everybody's, in some sense, seen this, right? So I'm not going to spend too much time on that. And then now I have to turn to the blackboard. Right. So what I decided to start with is just an example of a group. And of course the example chosen because it's the example that's relevant for both Strontium-Rutheniate and for actually high temperature superconductors. And so I'm going to look at the group here, D4, which means dihedral with a fourfold symmetry axis. And I'm just going to draw, it's a group of a square. And I'm going to draw a square here. All right. And then we're just going to go through the elements here. And the reason I do this is, even though it's a simple example, I'll be using some notation later on that comes out of this example. So it's just good to follow exactly how I'm defining these symmetry operations. All right. So let's begin with some elements of this. All right, so here's my notation for rotations. This means a rotation of pi by 2 around the z-axis. All right, so the z-axis is coming out like this. And that will take, let me just define an x-axis here and a y-axis here. So that'll take x to y, y to minus x, etc. And then we'll call this C4. So I'll use both these notations interchangeably. And then we can have following symmetry elements. This is a twofold rotation about the x-axis. We'll call that C2x. It takes this, keeps the x-axis unchanged and takes y to minus y. And then I think you guys could even tell me the rest of the symmetry elements here. So let me not take up too much space, but let me just write down. So C2y then is a twofold rotation axis about the y. And then I'm going to find two other axes. Actually, call this axis epsilon. Okay. Epsilon and eta. All right, and so then I have two more twofold symmetry axes. So I can draw all the twofold symmetry axes here as follows. All right. So this is the dihedral group. It consists of, well, how many elements? I haven't drawn them all here. No one's willing to guess. Sorry? There's 8 elements.
Do you also have reflections, mirror reflections?
So I haven't included mirror reflection here, and okay.
In D4 there are mirror reflections.
Yeah, so let's put the mirror reflection in here. I just don't want to write down 16 elements. Okay, but So I'm going to put in a mirror reflection, which I'll call sigma sub h, and that means that through the normal coming out of the blackboard here, I have a mirror symmetry.
Because for this chiral state, I think it actually matters a lot.
Yeah, it's, well, the fact that you can classify even and odd parity and between singlet and triplet, you need this element to be there. Well, okay, it's there, yes. All right, so I'm not going to pay attention to this mirror symmetry right now just for the sake of argument, but let me then write down all the elements of this group. So here are all the 8 elements. And one thing I want you to notice, which helps in defining the group in a more concise form, is that I can take this two-fold rotation axis here and write it as a combination of a four-fold rotation and a two-fold rotation about the x-axis. To see that, let's look at this axis here. If I do a four-fold rotation, I bring that over to here. Now if I do a two-fold rotation about x, I bring that down here. And you can see so that means that under these two operations, I take this vector to this vector. Everyone see that? That's the same as doing a two-fold rotation about here. And in fact, every element of this group can be written as a product of either C2x and C4, right? So this is C4, C4 cubed, etc. And so we call the two elements C4, and this is some choice. We call these the generators of D4. Because the choice is not unique. And so we can write the group D4 in a more concise form as the group made from the generators C4 and C2x that satisfy the following properties. C4 to the fourth equals C2x squared equals C2x C4 squared equals what?
1.
Yeah, that's right, the identity. Right. And so that's a concise way of writing it, and so you can already see that we can define another set of groups like that. For example, I can define the group C4 tilde as the group coming from the element C4 such that C4 to the fourth is just the identity. And in fact, I can define any n-fold symmetry axis like this. All right, so the reason I'm doing this is because I'm going to give a little problem. In case people are a little bit bored by lectures, they have something to work on the side. All right, so I defined a few groups here. And so let's give a little homework problem. Okay. Okay. Thanks. Well, maybe they can't do this. All right, let's define a group. Well, let's call it G sub 1. All right, and it has two elements, A and B. And all you know about this is that A cubed is the identity, B to the seventh is the identity, and then A squared B equals B cubed A squared. And so the question is, what group is this? And it's amongst the groups I've already pointed out here. Right, so it's one of these groups that I've defined, and so you can spend some time now working that out if you don't want to follow the rest of this. All right. Okay, so we've defined a group, and now what I want to talk about is group representations. All right. And so let's just define a representation. And then what I'm going to do is first define a representation, and then define irreducible representations. So I'll just make a comment. The group theory I'm talking about now applies to what is known as compact groups. So for example, compact groups and finite groups. So for example, the group of a circle would be a compact group, the group of a sphere would be compact. And then a finite group this is a good example of a finite group. And so what you hear here you can take to those particular applications. All right, so when I'm talking about representations, all right, so I'm going to use a short form, rep. I'm going to say a representation of the group G is a mapping, which we can define through D, which takes G, the set of n by n complex non-singular matrices. So basically we're going to define this as some sort of square matrices such that if G1 times G2 is G1, G2, let's make it G3 actually, to be clear. Then the mapped elements G1, D times G1, or so the matrix corresponding to G1, the matrix corresponding to G2, gives the matrix corresponding to G3. So that's a representation. All right, and let's look at a couple examples. Let's start with the simplest example. Let's look at this group D4, which we've defined here. Actually, let's do it simpler. I don't have to write as much. Let's look at the group C4. So that's just the fourfold rotation axis and all those. And let's look at rotations of a vector under the elements of C4. So if I rotate about the z-axis through an angle theta, then these are my rotation matrices. And so the way I'm going to construct a representation here is I'm just going to look at the rotation matrices for all the group elements, right? So there's 4 group elements, and so I can write those all out. And we'll do a couple of examples of these. All right. So let's call this representation formed by this, we'll label it V. And we'll start with the identity element. And so can anyone tell me what the identity element is going to be then in this form?
It's matrix.
Yeah. Use a matrix, yes. Yeah. All right. So that's the identity element. There's only 4 elements here, so I can write down 4 matrices. All right. Now, I'll just write these down. I think you guys can plug in pi 2 into here and get the appropriate matrices. And so that's my representation then formed from, so my representation V, and as you can see that these matrices will clearly obey the same properties as the group elements, right? So this element squared will give this, same with this element squared will give this, this element to the 4th power will give this, and so it obeys the same properties as the group itself. All right, let me talk about maybe a couple other examples. A very popular example, which is always existing. So another representation is where every single element maps to the element, maps to number 1. And this representation has a lot of names. It's an irreducible representation. That's something I'll define in a few minutes. But it's known as the identity representation. And in the context of finite groups like this, it's given the label A sub 1. I think it's spelled identity, right? Okay. And so an example of a basis for this would be something like x squared plus y squared plus z squared. if I apply any of the rotations of C4 to this, I'll get the same thing back. And so this would form a basis for this representation. And then maybe let's look at a superconducting example, which is also a member of this identity representation. But I thought I would take this example from Alex Gurovich's talk yesterday in iron arsenide materials. So, if you remember, there were electron pockets and hole pockets, so the Fermi surface was a bit complicated. And so here I'm going to draw, I'm just going to draw the hole pockets in kind of an extended zone scheme. So this is my Brouwen zone. Alright, so I should only define the inner halves of these pockets, but this half I can bring over here through reciprocal lattice vector, so I can make this a complete circle. Alright, and so this has one electron pocket and two hole pockets. And then one of the examples that were given of a gap function, which had formerly what's known as S-wave symmetry, well, two examples were given. One where this is plus and these are all minus. Right? And another example was where this had a D-wave-like form. So let me just draw something that's formally of this representation for this group here. Oh, maybe I should explain my, well, let me draw this first. And I'll explain what I'm drawing exactly in a couple seconds. All right. So this gap function is an example of the identity representation for the group D4H, which refers to iron arsenic. And it's quite non-trivial, as you can see, right? I mean, I've drawn here a plus order parameter. And these lobes, by the way, this means that the magnitude of the order parameter on this part of the Fermi surface is biggest and has a minus sign. Here the magnitude of the order parameter vanishes. Here the magnitude is largest and has a positive sign. And so as you go around, the gap is changing. Here it's big positive, here it's big negative, and here it's 0. So I haven't drawn the zeros very well, but there's zeros there. Alright, so this thing, if you look, if I apply a fourfold rotation, you can see it's invariant because this pocket will go to this pocket and these minus lobes will coincide, right? So under fourfold rotation, this has fourfold rotation. And so, and you can convince yourself that under any symmetry element, you'll satisfy, you'll find that this is true. It maps to itself under any symmetry element. So this is what's known as an S-wave state. So here's one of the things about the nomenclature of superconductivity. You know, when we see S-wave the first time, we're typically referring to a spherical potential, and we're talking about the lowest energy bound state in a spherical potential, right? And so that really is like a sphere. But here, we loosen that to talk about discrete groups and call things like this S-wave as well. And this happens quite a lot in this field. And so you'll see that there's an infinite number of choices I can make for an order parameter that has S-wave symmetry here. All of them are used as S-wave in this field. Right? And that's just because it's maybe too complicated to explain the rest. Right. So this is an example then of an identity representation in a superconducting state. Alright, so now I'm going to go on over here. Now what's the best way for me to get rid of the screen, the light? Maybe. If I switch it off, it'll take a long time to switch on.
Makes the screen black.
Yeah, I was wondering maybe I can, maybe if I put an innocuous background. Maybe I have a nice, almost empty slide. Let's just see. Alright, well, if it's tall enough, I could just put a piece of paper up there. Yeah, maybe that may be good enough, right? I don't know, people should be able to see this. Are you just switching the channel? That might be enough.
I think it turns down if you push the power button twice, so at some point it asks if you want to press again.
Alright. I think this will work, right? I can right here. Alright. So what I've given you then are examples of representations And so now what I want to talk about is, you can see quite clearly that if I define a representation here, that this definition is not necessarily unique, because I only need to satisfy this rule here, and I can apply just a similarity transformation to each of these matrices, and the rule will still apply. And so that leads to the definition of equivalent representations.
Excuse me, for the new types, is the lattice actually cubic? So can we even use this D4?
Okay, I'm being a little, okay, it's, okay. So
No, it
it is tetragonal, but I'm just,
Yeah.
Alex showed this example yesterday. I thought it was a nice example to drive across the point that definition of S-wave is highly non-trivial in this field.
But has it actually been done, the classification of the symmetry?
Oh, it will have been done. I think in the case of pictides, it's been done more so than in much more detail.
Oh.
All right. So, you ready? I think you guys know where I'm going with this. So 2 reps, D1 and D2 are equivalent. If D1 of G is S for all G in the group. All right. So this just simply says that if I take some constant matrix, multiply every element in D2 by S on one side and S inverse on the other, then this S is independent of G, then I will have 2 equivalent representations. All right, and you can see where that comes from. Again, if I put an S here, S to the minus 1 here, S inverse here, I'll get SD S to the minus 1 here. Right? So this says that these representations are not unique, and so what people do then to get rid of this possibility, or to classify different representations, is they take the trace of the matrices. So the trace, as you probably all well know, is independent of such a transformation. Right. And so I'm going to define the character of a representation. And let's just let the character defined for each group element is just the trace of the matrix D of G. All right. And so I should be careful. Let's define chi of G as the trace of G of G. The set of these traces is the character. Of the representation. All right. So why is this called the character? Well, it gets rid of this problem that if equivalent representations show up, then we have a unique identifier for theirs, and so in some sense this characterizes the representation. So that's where the name character comes from. All right. And so as an example, all right, let me just give an example. Let's look at this representation labeled by V. And I can write down all the characters. And so what's the character for the identity element? You guys can all take a trace of these matrices, right? And so we can write them all down. Did I take those right? My equal signs on my notes looks like a minus sign, so those are all right, right? These characters? Yeah.
We
those are
can't
right.
tell anyway.
Sorry?
We can't tell anyway.
Oh, because of the markers?
Can't see it.
Okay.
Let me
try it. 3, 1, minus 1, 1.
So is the dimensionality of representation matters, does it matter in this case? Because for instance, I could imagine two identity representation, three-dimensional, two-dimensional. They will have all these different characters, 3 and 2, but obviously they're equivalent
Yeah, so
representation.
we're going to go into that. So I've defined the representation, that's why I'll label it by sub p. And you'll see, you'll have your answer in a few seconds, actually. All right. All right. So let me just make the statement without writing it down. That then, so two equivalent representations have the same character, but if two representations have the same character, they're equivalent. So the converse also holds for that. I won't write that down. And now I'll go on to define reducible. And a representation is reducible if you can write it for every single group element in the following form. So, for every single group element, if you can write it as block diagonal form for all G, then this representation is said to be reducible. If it's not reducible, then it's irreducible. And so irreducible representations are the basic building blocks of group theory, or of all representations. You can decompose any single representation into a sum of irreducible representations. So in answer to your question, I could have a representation that consists of 3 identity representations, and that would just be 3 copies of the same thing, but they would then all have 3 as each one of these characters.
But if you apply similarity transformation, you can make the 0 non-zero.
Yeah. So if there exists some basis in which you can write this in this form.
Yeah, so you have to specify the 2.
Yeah, you're right. Yeah. So if D and G can be written in this form for all G and G, then, well, I won't specify it but it's understood. The if captures it. And so otherwise, all right, so let's do a little problem.
Can I ask you a question?
Yes.
So if 2 representations are equivalent, there is a similarity transformation? You can prove that way?
Yes, that was the statement.
So mathematically you can prove that they exist, the similarity transformation?
Yes.
Okay.
Yeah, so I had that to write down, but I fear I'm taking too much time writing things on the board. Maybe that's good, maybe not. All right, so let's look at this representation here and ask, is it reducible? So can anyone tell me the answer?
Yeah.
It is reducible, and why?
Because you only need a 2-dimensional representation to represent these rotations.
Yeah, in fact, it already has this form, right? Yeah, the z-axis component is clearly got 2 zeros on the off-diagonal elements, and so I've written it in this block diagonal form right away. So this representation is indeed reducible. It breaks off as a basis element for this portion. Basis element for this is the z component, and then a basis element for this other block here are the xy components. And in fact, it turns out that for this group D4, this upper block here, oh sorry, this is for C4. Yeah, okay, so for C4, it's also true for D4. But in D4, this upper block will remain irreducible, means that we cannot further subdiagonalize that so that for every group element it's diagonal. But for the group C4, you can actually block diagonal, make each one of these diagonal. Right? And in fact, the basis functions that make them diagonal are x plus iy and x minus iy. And if you look at that, you'll get a block diagonal. You'll get a diagonal matrix for all of these. Right. So now you see what representations are. And I'm almost finished with this bit now. So in general, any representation d of g can be broken up into irreducible representations. And so here I'll denote the irreducible representations by a superscript. And then, without going into further details, there is one useful formula which lets you do this. So if you know the characters, characters for different representations are orthogonal in the sense that if you sum over all group elements, you get this delta function. And so you can use this orthogonality relationship to decompose this representation in all the basic representations you need. So you can find all these coefficients, a sub mu, from using this orthogonality principle. This is like what you do with spherical harmonics as well. Right? You decompose a function of spherical harmonics, you can use a similar orthogonality relationship. All right. So what's been done then is it just tells you what representations, what irreducible representations are, how they're defined, and how you can understand them. And the important point is that we're going to use the irreducible representations to define the possible pairing symmetries that show up in a system, particularly in a finite system. All right. And so now I want to go back to the screen. How long have I taken actually? Let's turn this. So how do I do this? I just want to turn this back on again actually. Alright. So now I want to talk about classifying gap functions. And so here I've written down the character table for the group D4, and maybe slightly different notation, but this is a twofold rotation which I called C2Z. This is C2X, and this is C2 epsilon and C2 eta. And then these are C2X and C2Y. Alright, and so notice the factors of 2 here. I'm not going to describe why they show up, but this means that both the elements C4 and C4 cubed have the same character, and the elements C2X and C2Y have the same character, as do C2 eta and C2 epsilon. They both have the same character. And so you can write down all the possible representations, irreducible representations you have for the group D4. There's 5 of them. And so what this means in the context of superconductivity is it means that you have 5 possible pairing symmetries that can show up. And if you look at all these one-dimensional representations, meaning that under any group element they just pick up a plus or minus 1, then you can see that the actual Ginzburg-Landau theory in that case is going to be, well, I haven't shown it, but it turns out the Ginzburg-Landau theory in those cases are identical to the usual conventional Ginzburg-Landau theory. So for all these other representations, you have the same Ginzburg-Landau theory. The type of case...
Question.
Yeah.
But in these other representations, you're breaking not just gauge invariance, but also some discrete symmetry.
Yeah, you are, but the Ginzburg-Landau theories will be the same. Okay, then they will be up to... If you truncate at 2nd order in spatial variations and to 4th order in nonlinearity, then they'll be identical.
Okay.
In a second you'll see why, actually, because I'm going to talk about how you derive the free energies using this information. All right. And so I'll talk a little bit about these other examples. I'll focus on this example a little later on to show you what it means. And then we'll also talk in a lot of detail about this example here, which is the 2-dimensional representation. And the simplest case, that can be spanned by a basis which contains the x and y vectors, or px and py. So you can see why it's important.
It's 2-dimensional real representation, right? It's not complex.
I mean, here I've defined, it's real, yeah, but I mean, you could call it x plus iy, x minus iy, and define, and then the vectors, and then, I don't know, I think, in principle, it might be possible to find some unitary transformation that makes the elements of the representation complex. I haven't checked that, actually. Maybe they still remain real, but I haven't checked. Do you know the answer?
Yeah, I think it's important to, to have two-dimensional real representation to be able to build, you know,
I
type
see.
UI.
Okay, okay.
And for instance, for continuous group, if you just have not a lattice, but just a continuum model, you have basically a group of rotations. So every representation apart from, you know, S weight is two-dimensional real representation.
I see. Okay, well, certainly you can write this representation through purely real matrices, but I don't know, it may be possible to do some unitary transformation that makes some item checklists. So I'll squeeze out of that question a little bit. All right. Okay, so now I've defined representations. Now we can talk about the Ginzburg-Landau theories. And here's an answer to your question. So for the one-dimensional representations, this defines the transformation properties under particular group elements. So for example, for this representation here, if I apply a C2x or C2y, I must pick up a minus sign. For this element, I must pick up also a minus sign. The other ones must remain the same. And when we construct Ginzburg-Landau free energy functionals, the requirement is that these must be scalar under all the group operations. So right away, we require these are, there's a gauge symmetry here, and so we require that the free energy does not depend on the phase, and that means that I get the magnitude of this complex variable squared showing up everywhere. Right? That's the requirement of gauge symmetry. And now you can see that if I have under a group transformation that this picks up a minus sign, then this free energy is still unchanged, right? This is unchanged under psi goes to minus psi. This is also unchanged under psi goes to minus psi. And so you can see that this free energy must be the same for all the one-dimensional representations for that reason. Now for the two-dimensional representations, things get a little bit more complicated. And just to show you, not much more. So, just to give you an example of how we construct such free energy functionals, here I've told you that these are the terms that are allowed by symmetry that are non-zero. So these are the only possible nonlinear terms you can have. All other combinations, say a to x cubed, a to y, cannot appear. And I'll just go through a simple argument to show you how that happens. Let's consider in my free energy if I have a term, so a to x squared, a to x complex conjugate, a to y complex conjugate. Right? And here I'm imagining that the basis is px and py, or kx and ky. All right. And now you can see this is gauge invariant because if I apply a phase transformation e to the I theta, these two complex conjugates will cancel that. But now if I look at the element, say C2x, then this takes...
It's very hard to read.
It's very hard to read, huh? Maybe try another... Oh, the blue pen was good.
No, because there's a reflection there.
So, if I'm matching these like the x and y components of the vector, then the twofold rotation about the x-axis keeps x unchanged and changes the sign of the y component. Now, I'm going to require that my Ginzburg-Landau free energy is invariant under this transformation. Right? So now, if I apply this transformation to here, let's give this term a coefficient. Say, well, let's call it epsilon again. So if I now apply to this invariant, or this term in my free energy, this in principle possible term in my free energy, this symmetry property, what will I get? So if I do the C2x transformation, what will I get? Yeah, you get a minus sign. So I get. Right, because the y component changes sign, but the x component does not, and there's a single y component. All right. So the requirement that this is a scalar means that this must equal this, right? The free energy before and afterward must be equal, and that tells me what for epsilon? 0, right? So this implies epsilon 0. And so by considering the most general such term in your fourth order nonlinear portion, you can then write down all the terms that survive the symmetry elements. And the statement is that these are the only 3 that survive, in that case there. Right, so that gives you, and this is actually generally how Ginzburg-Landau theories are done. So how am I running way over? Maybe I should take how much more time?
As much as...
Well, let me finish. The longer the better. Let me finish this example here, and then when we go to deriving the, well, I'll continue with the rest tomorrow maybe. All right, so now that we have these possible coefficients in our Ginzburg-Landau free energy, when we want to find the ground state, we no longer have a unique choice like we did in the conventional superconductor. So in principle, if I vary these coefficients, and I take the derivative of what's in here with respect to eta x and eta y, and look, if I look for the ground state minima of this, with respect to eta x and eta y, depending on these coefficients, I can have different choices. And so you guys can minimize a polynomial, so I'm not going to go through that. But you can then look at the possible different ground states that show up. And it turns out there are 3 possible different ground states, which are distinct by symmetry. So I've shown them here. This has to be positive, so you can divide B2 by B1 and B3 by B1, and then draw a phase diagram for all the possible values of B2 and B3. And then you see that there are 3 possible phases. So in this phase, this is 1I, and this is the px plus ipy state I was talking about before. In this phase, this is px plus py, and this phase is purely px. And so what does that mean for gap functions? Well, these are actually very different phases. Px plus ipy is gapless, at least in the most simple cases. Px vanishes along the line kx equals 0, so that has nodes. And so it vanishes, which means it'll have different low temperature properties. So these 2 phases will be easily distinguishable through experiments, like you mentioned earlier, so there are some caveats. And then this phase will just have the nodes rotated by 45 degrees. Kx plus ky is just 45-degree rotated kx. Ignore what's down here. And so the Ginzburg-Landau theories give us 3 phases, and if we want to now address which one of these appear in reality, we have to find some way of specifying these coefficients. And so the next step of the program then is to specify these 3 coefficients, or in particular these 2 coefficients, to see where do weak coupling theories put us in this phase diagram. And so maybe, as my last statement, I'll tell you what the answer is before we go and derive it. It turns out that for any arbitrary shape of Fermi surface and any arbitrary gap function, so I told you there's an infinite choices, px and py I've been using, but I could say use as an x basis element px squared times px or px cubed and py cubed. There's many choices I could take. For any arbitrary choice and any arbitrary Fermi surface, you find that you always lie in this phase here. And actually, the reason weak coupling theory is very easy to understand is because it has actually no zeros. And weak coupling theory wants to use as much of the low density of states as you have as possible. And so it'll always try to lie in this phase. There are a couple places where it lies right on the boundary between these 2 phases. And we'll talk a little more about that in the next lecture on this. So I think that's probably a good place to stop for now. And then I'll go on with this next time.
Thank you very much.